First of all, so thanks to Radu and Yura for organizing this nice workshop, and also for the online version that was nice during COVID. So today I will try to entertain you on the topic, actually on something that's somewhat related to the things that I discussed during the online version. In particular, I want to entertain you on the topic of Lyapunov analyses and how we can search for them in a principled way. So actually, before starting, so let me say that it was, I will do the baby versions of the things we did with great colleagues. In particular, Pontus will talk in more details on less baby versions, let's say. So I still call them baby versions, sorry. Actually, so what I will present is essentially, you can essentially find it in works we did together with Laurent Lessard and Brian. And at the end of the presentation, if I'm not out of time, I will discuss quickly things we did together with Baptiste and Emmerich. And if you are interested, so actually I will focus on a simple setting where everything converges nicely, exponentially or linearly, depending on who you talk to. But if you are interested in a sublinear setup, you can check the things we did with Francis. Okay, so before starting, let me say that actually, so this is related to a topic that actually was launched, let's say, by two main papers. So first, a paper by Yoel Rory and Marc Teboul. So I think Marc will not talk about it. So, but and then a paper by Laurent Lessard, Benjamin Rex, and Andrew Prakar. And essentially, I will do the informal link between the two things. So essentially, this first approach typically is somewhat reproached to be time-depending, well, to have to study, let's say, large semi-definite programs in order to study performance guarantees for optimization methods. This one actually is more restricted toward linear convergence, but studies like actually smaller, more tractable semi-definite programs. So we'll see how they essentially relate. Okay, so if you are interested, this is essentially where you can find the details. And if you want, actually, if you are interested in the general topic, let me say that actually we took some time to try to make packages where you can access and play with those things quite easily. So actually, in the most recent version of Pepit, so it's in for performance estimation in Python, you can find like maybe 75 examples of things. But what if you can do with them? So if you actually have example of algorithms that you think are worth analyzing with them, please don't hesitate. Just we can have a chat and we can add them to the list. I'm very happy to do that. Okay. Okay. So let's consider like the setup that we will that I will try to entertain you with during this half an hour. So we'll take the most standard simple setup for optimization with linear convergence rates. So we said that we want to minimize a smooth, strongly convex function. So I will spend 20 seconds on that on the next slide in case someone doesn't know what it is, which I think is perhaps not the case. And I will take like the most baby versions of the algorithm that we could use for that. So essentially gradient methods, possibly with some history, okay? But the important thing is that typically what I will require is that the algorithm is stationary, okay? So I don't want the parameters, so alpha, beta, and gamma, to change along with the iteration. So we can discuss that afterward if you want. And the second thing is I want you to give them to me beforehand, okay? So they are predefined and they don't change along the iterations. Okay, so actually this includes the stationary version of quite a few algorithms that we are probably used to. And then a question here is that of, okay, when we have such a thing, how do we establish convergence of such algorithms? So the typical answer is that we actually use what we call Lyapunov analysis. And in this talk, so I really want to try to emphasize what a Lyapunov function should look like when we study such algorithms. Okay, so in case you don't know, just in 20 seconds, I promise. Because this is a setup we study, so we said that the blue function, so the differentiable blue function is smooth and strongly convex. If, so first, convexity, I mean that if we do first order approximation, we get global linear underestimate of the function. By strong convexity, I mean just that if we add a bit of curvature, so mu to that linear underestimator, we get a global quadratic lower bound. And by smoothness, I mean the complementary thing. Essentially, if I take the first order approximation and I add more of curvature, I get a global quadratic upper bound on this function. Okay, so that being said, what do I want to convey as a message? So first, what's the first thing is that actually we can cast the problem of finding Lyapunov functions as a quasi-convex program, essentially, for such methods. The second thing that I want to informally stress on is the importance, actually, of the choice of the inequalities we use when performing the analysis. Okay, so essentially the talk is divided into 4 main parts. So I think that we should not be out of time, but okay, so first I'll just go back to what is a Lyapunov function, okay, in order to have a clear definition of what we are looking for. Then I want to stress, okay, how do we actually look for Lyapunov functions? And then, okay, so typically those things, we do them by hand when we do classical performance analysis. So a natural question is, okay, if we cannot find a Lyapunov function, actually, when should I stop searching for something actually to prove convergence? Okay, so essentially, if the first part doesn't work, what can we say about the method? So either should we search for something more complicated, or should we stop looking for something? And so this is when about, okay, let's say, argument for saying that you should stop looking for something. Okay, and then I conclude. Okay, so first, what is a Lyapunov function? So let's say we have a dynamical system. So I denote by psi k the state of this dynamical system. I said that a dynamical system with a fixed point, that's a psi star. Okay, so typically what we want to do is to study the stability, or essentially the convergence of this sequence of states, okay, provided by the dynamical system. And for doing that, typically what we do is we rely on a notion of, we try to find Lyapunov function which correspond to certain notions of energy. And what we want is this energy to decrease along trajectories. And so the idea is to try to, instead of studying like the whole sequence, to reduce the analysis to only one iteration of the sequence at of the algorithm at a time. Okay, so what should actually Lyapunov function satisfy in order to make us happy with that? So actually there are many different variations around this definition. So we can actually tailor them for different purpose. So the one I will take here is the fact that, so as a Lyapunov function, I want actually that it is always positive. Okay, I want it to be 0 only if I evaluate it at the stationary point, so at the fixed point of the process. And then, okay, so this is just the fact that I want it to be lower bounded by something that is of interest to me. So I'll come back to that. And then I want it to decrease along trajectory, and here I want it to decrease exponentially. Okay, so why is that nice if we get this? So actually for the whole talk, I will stick with this notion of lower bound as this thing, because it is easy. So it might actually not be the thing that you want. Actually, you can change it and redo the whole thing. Okay, so if we pick that, the nice thing about having a Lyapunov analysis like this is that you can just iterate that, okay? Iterate the Lyapunov inequality, so we obtain that this thing converge to 0 exponentially. And then if, in addition, this thing is lower bounded by like this, it means that we can say something about the distance between the current iterates and the fixed point, okay? Okay, so again, let me say that there are many variations around this, for instance, and in particular in the case of optimization algorithms. That's so good. So please don't interrupt me if you have questions. Okay, so let's go back to what we wanted to do. So let's consider the simplest algorithm ever, gradient descent. So for gradient descent, actually, it's very natural to say that the states that we want to consider consists of all the information that we are aware of at the current iterate. Okay, so the states, naturally, we can say that it consists of the xk. So let's say that we normalize it with that take xk minus the fixed point. Then we also want typically to have the gradient as a state and the function values. Okay, and then if we do that, the optimal the fixed point is this thing, is 0. Then naturally, actually, when we do Lyapunov analysis, what we choose are quadratic Lyapunov functions. So it's also natural to choose this thing. So, okay, it might look quite not natural. Actually, this thing is just to make sure that actually the Lyapunov function is isotropic. So you measure things in the same way in all directions. So you can think of it that way. Okay. So essentially, you have one component with the distance toward the solution, one component with the cross product between gradient and distance, and xk minus x star, and then you have so gradient and function values. Okay, so the typical approach when you do Lyapunov analysis now, if you go back to your classical linear system analysis class, is to choose P to be, actually to satisfy the previous condition, we choose P to be positive definite. Okay, so here the point is, typically, if we choose P to be positive definite, do we lose something? Actually, the point is, there are very a priori valid P's that are not semi-definite programming, that are not semi-definite, positive semi-definite. In particular, for convex optimization, you can think of this thing, this term alone. So if you put this one off, this one off, and this one off, actually, it's positive because we are working with a convex function. But it corresponds to the non-positive definite matrix P. Okay, it corresponds to only like the non-diagonal elements. So should that be a valid Lyapunov function? Okay, so in a sense, what I want to do is two things. So I want to find condition under which, so the first, so this is what I will call positive semi-definite for the purpose of this talk. So I want essentially this thing to be lower bounded by some notion of distance that I choose. So for all x, for all dimension, and for all smooth-only convex function. And also I want the Lyapunov function to decrease along trajectories geometrically. Okay, so those are the two things I will focus on. Okay, so how do we verify this? So I'll first focus on this condition, then I will say a bit in a more hand-wavy fashion that actually the second one, we can just adapt the argument for the first one to the second one. Okay, so how do we verify this thing? So what we want to do is to verify that essentially this is true. So we want to verify that when we are sufficiently far away from the stationary point, actually the smallest possible value of the Lyapunov function is larger than epsilon, is the distance. Okay, so probably you see where I will actually go if you went over there at the online version. So actually, this is an infinite dimensional problem. So I'm working on a class of smooth-only convex function. And so a natural idea is to just sample the problem. Actually, the function, the important point is that the function here is used only at 2 points. So actually, we use the function only at x and at x star. Okay? So the natural thing to do is to just discretize the problem at those 2 points. And okay, so let's do that. So essentially, I remove artificially the fact I work on functions by working on the discrete version of the function with only 2 points in the discretization. Okay, so in order not to lose anything, what I do is I require that there exists a function that essentially explains my 2 points. Okay, so essentially that interpolates the 2 points that I sampled. Okay, so here I did not change anything, obviously, because I replaced the infinite dimensional problem here by somehow infinite dimensional constraints. Okay. So but naturally this gives rise to something where we work with different variables. Okay, so what can we do with that? So for those who already saw it, I will do as if you didn't know. Okay, so essentially we can resort on what we call interpolation or extension result, saying that so if we have, so essentially what we want to find are conditions under which so those point x, those subgradient and FIs are indeed correspond to subgradient and function values at the points at those xi for a certain function that is smooth and semi convex. So very quickly, actually, you can find, and we actually obtain, so that actually this thing, so the condition for those points to be interpolable, you can just require them by using a specific inequality, which is this one, which is essentially quadratic, so which you have to require for all pairs of points, and which is essentially quadratic in the gradients and the x, and linear in function values. And if this looks a bit much, actually you can just think of it as if you fix mu to 0 and L to infinity, you recover just convexity. Okay, so all in all, what we can do is just replace now those things by, so we have 2 points. In order to not lose anything, I just have to replace the discrete version by, well, the inequalities between all pairs of points. So what I can do is just replace this condition by those 2 quadratic inequalities. Okay, so obviously I did not change anything. If you believe the result of the previous slides, actually all feasible points to the new problem actually correspond to feasible points to the first problem and vice versa. So you can convert so feasible points, and you can check that actually you do not change the value of the objective by doing that. So we are fine. Okay, so actually now I'll just go for the, okay, how can we actually verify this thing? Actually, so, okay, sorry, one thing that I've somewhat hidden from you, perhaps a bit, is the fact that I want this result to hold for any dimension. So I'm optimizing over also the dimension. And the convenient reason for doing that is actually that you can cast this exactly using semi-definite programming, so without doing relaxations. What do I mean by that? So essentially, now instead of working, if you accept that instead of working with x and the corresponding gradients, you work with this matrix, which is PSD as a new variable. Actually, the previous problem is actually a semi-definite program, which is linear in G. You can, so please bear with me. So this, I hope you can trust me with this. You can really reformulate the previous problem exactly like this. And just so to check, so actually the P here and the P here, they really correspond to the matrix for the Lyapunov function that we had before. Okay, so what can we do with that? So first, a few things. So actually, you can check that this is homogeneous in epsilon, so we can fix it to 1 arbitrarily. Okay, and the second thing, which is more convenient, is the fact that this thing, you can verify that there is a Slater point. Actually, this is a simple exercise because we just have to verify that there exists a feasible point with full rank such a matrix. So it's kind of okay. So where do I want to go with that? So now, if you bear with me a bit with the notations, you can actually reformulate that as a standard semi-definite problem, and you can go for the dual version of it. Okay, and we said that. So if you believe me that there is no Slater point, actually, you can believe me that there is no problem in doing that. So if you go to the dual, you can observe that we end up with something like this. So the only message here is that you can just actually you have a semi-definite argument actually that you have to check only for tau equal to 1, saying that okay, P is a valid Lyapunov function if only if this is true. Okay, so let me say it in words that maybe we are more familiar with. Actually, if you go back to the original question, what does it mean? It means that essentially this Lyapunov function is a valid Lyapunov function, so it's positive definite, if and only if you can rewrite it as something like this, quadratic terms, plus actually the inequalities that we had before. So essentially, what does it mean? It means that you can allow for non-positive definite matrices in the original version of the problem, so of diagonal elements, if and only if you can compensate those diagonal elements with the two inequalities that we had. Okay, so it means that essentially, so that this is what it means. Okay, and those two things, they are positive. Okay, and then because of the thing that we choose to require on the Lyapunov function, actually we also have those conditions. So good. Okay, so actually we were not interested only in gradient descent. We were interested in something a bit more, let's say, fancy. Okay, so actually you can do exactly the same steps here with this Lyapunov function, with this method. Naturally, you can think of, okay, I can just put everything I have at the locally at the current iteration in this Lyapunov function. And actually, the consequence is that actually this is a valid Lyapunov function if and only if you can compensate it, compensate all the non-classically positive definite parts, so in the usual quadratic sense, by actually interpolation inequality. And if you redo just all the things we did together just before, actually you can remark that here, instead of having to discretize 2 points, so xk and the optimal point, we have to discretize 3 points and require for the problem to be, well, for following the same steps, that the inequalities are valid for all pairs of points in 3 points, well, in essentially a set of 3 points. So what does it give? It gives that at the end you have 6 inequalities that you are allowed to play with while actually constructing your Lyapunov function. Okay, so if you bear with me now, I'll just say, okay, now what can we do for searching for Lyapunov function? Because now we just have a condition ensuring that the Lyapunov, well, the candidate Lyapunov function is positive. Okay, so essentially, now what we can do is, let's say that we choose the Lyapunov function. So now what we want to do is just to check that it satisfies this inequality, okay, for a certain row. So as before, what we want is this inequality to be valid for all function, all dimension. But in addition, we also want this inequality to be valid for all xk and xk plus 1, given that xk plus 1 is generated by the algorithm you want to study. So in a nutshell, what you want to do is just to verify that this is true. So okay, so this is true with those constraints. So now I will be even more unwavy. So actually, this problem, you can just go to the exact same step as before for realizing that actually you can also verify this using semi-definite programs. Okay. Okay, so the variable here are originally f, f and the hit rate. So actually, by the way, even for gradient descent, it means that we have more points to consider in our discretization when we go to the different steps. So it means also more inequalities. Okay? And the parameters are all of those. Okay, so in a nutshell, so you just have to sample at 3 points. So even for gradient descent, so you have 2 inequalities to verify that the Lyapunov function is indeed positive, and then possibly 6 inequalities to verify that it's decreasing along trajectories. Okay, so you have an SDP with 6. So essentially, perhaps, so I will be fight on this, but essentially the good news is that actually this is also, well, you can also formulate it using linear matrix inequalities, which are linear actually also in the coefficient of the Lyapunov function. And at the end of the day, what it means is that you can search for efficiently, so given all the parameters that we have in the problem, so essentially the strongly convex constant, the Lipschitz constant, the parameter of the algorithm, so the step size and the convergence rate that you want to verify, essentially searching for the Lyapunov function, it can be done via actually 2 LMIs. Okay, so one for verifying this condition and the second one for verifying this one. Okay. Okay. So in order now to check, to actually optimize and check what is the best convergence rate that you can verify for which you can find the Lyapunov function of the previous thing, what you can do is just actually do a bisection on row. Okay, binary search on row. Yes. Okay. Just a few examples. So here I will show what you obtain using exactly the approach. On this one, I will show what you would obtain if you would instead directly require that P, well, the Lyapunov function is positive definite in the usual quadratic sense. Okay, so actually for gradient descent, it doesn't change anything. For heavy ball, it doesn't change much. Actually, it changes a bit, but anyway, the method is not proved to converge. Okay, for fast gradient, actually, we can, so Nesterov's method, typically, it changes a bit, but it's not very visible. And perhaps more interesting, actually, if you consider now the ultimately optimal method for smooth strongly convex optimization, you can see that doing that actually totally fails. And in order to be able to capture the convergence, you really need to consider that the matrix should be positive, possibly not positive definite. Okay? Yes? Sorry? I did not. Yes? 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 Actually, it will optimize the convergence rate. So the convergence rate can be, so in fact, between the difference between those two is power 2. So essentially, Nesterov not totally match the lower bound, and this one actually totally match the lower bound. But this is a matter of essentially constant in the. It will be 1 minus square root kappa, all of these squared. So this is, yes, thank you for your question. Okay, other questions? No, okay, so just to recap, the King, sorry, you had a question? Oh yeah, you can, actually this is how this one was designed. Yes. No, it's typically, for this setup, it's typically quadratic in, well, you have bilinear quadratic problems. So, but no, not for the parameters. No. Actually, you could for gradient descent, but perhaps not very. So actually, for this precise setup, this is done, and this is the answer. So the Vanscoy actually totally match. You cannot improve it by any way, and actually we also, so you can adapt all of this, also design lower bounds. And actually, with this one, we show that there is a matching lower bound. So for this precise setup, so smooth only convex optimization, this is closed, and this was done actually by optimizing such SDPs. So thank you. So yes, yes, yes. So essentially, so totally right. So actually, in the so there are different stochastic setups. So the finite sum, where actually you will. So we have the same. Sorry. So in the stochastic setup, you need to optimize over the trade-off between gradient noise and this convergence rate. Yes, totally. Okay, I don't know, but certainly. So that's a good question, and we can take it afterwards. Really, this is for the as I told, this is really a baby version. Okay, if you wanted to make actually what is really difficult is to make it adaptive. So to take alpha, beta, and gamma that actually adapt to what you observed in the previous iteration. That's really difficult. Time varying is not very difficult. It's just that you get larger SDPs. Yes. Okay, so let me just recap. Essentially, what we had, the key ingredient as that actually what made those things easy is the fact that we can describe the class of function with simple quadratic inequalities, okay, which turn out to be interpolating inequalities. Okay, so 4 minutes is okay, you are? Yes, okay. Okay, so essentially, this is also because we studied here stationary first order method, but we can adapt that. And we have only considering actually quadratic Lyapunov function. And if you go for adaptive method, typically, probably you should not consider quadratic Lyapunov function. Okay, and then the idea is that if you do that, you will obtain like the best Lyapunov function that is essentially of a given structure that works for all smooth Rondi complex functions. Okay, so actually, just a quick message for that. Please do not read this. The only message is that actually, if you study optimal methods, you will see that typically those methods, they need, in order to prove convergence, Lyapunov function with that kind of structure. Okay, and in particular, so for the last one, so you can see you can obtain like all the results in the nice paper with Ernest. Okay. Okay, so just in order to very quickly do the remaining slides. So actually, in the case where you don't know, you just have inequalities describing your class, but those do not have like the interpolation principle. What you can do is just put it all in your SDP and just cross fingers that it will give you something. Okay, but it's just actually corresponds to doing relaxations. So now the question that I want just to quickly give a preview on is, okay, what happens if actually you do that with your favorite first order methods and you do not succeed in doing that? So for instance, because actually you find unsatisfying convergence rates larger than 1. So first idea is actually that you could consider like broader class or different classes of Lyapunov function. A second idea that I think Benjamin will talk about is actually to consider like longer time horizons. And this is essentially what was done for studying gradient descent with larger step sizes. And then the last thing is, okay, but when should I stop looking for more if I cannot succeed obtaining a good, well, satisfying performances with that? Okay, so actually, so what we showed is actually, well, what is known is when you have a Lyapunov function in Lyapunov function satisfying the initial assumption that I made, it's a sufficient condition for linear convergence. So what I want to use now is that if there is no cyclic trajectory for your algorithm, if there exists no cyclic trajectory, actually this is necessary for convergence. And actually you can use the exact same tool for looking for instead periodic, let's say, trajectories. So let me just do it very quickly. So if you consider actually the EV ball method, you can actually cast the problem of looking for cyclic trajectory as an SDP, actually using the exact same steps, just that you have to care about the thing. Actually, if you want to benefit from actually solving this SDP is quite painful, but if you are careful and you use all symmetries that are in there, actually you can reduce it to an LP in that case. Okay, but what does it give? So essentially, those are the two parameters of the EV ball method. So this is in this green region, we were able to actually show that there is a convergence rate smaller than 1. Okay. So the question is, what can we do outside of this region? And actually, if you apply the technique of actually looking for cycles, what you can see is that actually inside of those regions, except of very small gaps, typically you cannot do anything. Actually, for when you study one iteration at least. And perhaps the not surprising news is that if you consider quadratic optimization, typically this is the point that you consider, and it's clearly largely outside of this set. Okay, so actually the cycle for this particular tuning was obtained before by Laurent Lessard and co-authors. Okay, so let me conclude. What we did was to study essentially the structure of arising from Lyapunov analysis when you consider simple optimization methods. So I hope I convinced you that actually you should not directly take the standard idea that you should look for Lyapunov with positive definite matrices. Okay, so this gives, and actually what we did gives like sufficient condition for global linear convergence. So if you are not satisfied with the result you get, so for instance, it's not guaranteeing convergence, what you can do is instead look for cycles. Okay, and maybe another thing that is important, so at the end of the day, converting that to actually closed form solution, analytical solution, so going from the numeric to analytical solution, it's not always easy, typically it's not, and and so this is really part of the cost we have to pay for doing that. Okay, so actually, important point that we already mentioned. So adaptive methods, we can really not do anything with them currently. Well, not much. Actually, it's the same when you consider non-Euclidean methods. So for example, mirror descent and fixed-lat. So there are things that we can say, but they are pretty weak. So we can discuss them after if you want. And also, like for instance, higher order methods are things that we would naturally want to study using those kind of things, but we cannot do that currently, at least not directly. And if you are interested, please don't hesitate to make contribution, make contribution or give feedbacks on those packages. And on this, I will just thank you. And if you have more questions, I'm happy.